Albert Einstein, The Mind That Changed Our Understanding of the Universe, Part 1, The World Before Einstein. At the end of the 19th century, physics appeared to be nearing completion. Isaac Newton's laws of motion and gravitation, formulated more than 200 years earlier, had successfully explained the movements of planets, the trajectory of cannonballs, and the swing of pendulums. His mathematical framework had become so reliable that astronomers could predict celestial events decades in advance. The Industrial Revolution had transformed European society, and scientific progress seemed unstoppable. Physicists had developed powerful theories about heat, energy, and the behavior of gases. They understood the conservation of energy and had mapped the laws of thermodynamics with precision. In the 1860s, James Clerk Maxwell had unified electricity and magnetism into a single elegant theory, describing light itself as an electromagnetic wave. His equations predicted that light traveled at a constant speed through space. This discovery was hailed as one of the greatest achievements in physics, comparable to Newton's own work. By the 1890s, many leading scientists believed that the fundamental laws of nature had been discovered. Lord Kelvin, one of Britain's most distinguished physicists, remarked that the future of physics would consist mainly of adding decimal places to existing measurements. Yet beneath this confident surface, troubling questions remained unanswered. Maxwell's equations seemed to require a medium called the luminiferous ether, through which light waves traveled, but no one could detect this mysterious substance. Experiments designed to measure Earth's motion through the ether had failed inexplicably. The nature of light itself remained puzzling. Was it a wave or a particle? Classical physics could not explain why heated objects radiated energy in specific patterns, a problem known as blackbody radiation. The precise orbits of planets showed tiny anomalies that Newtonian gravity could not account for. These were considered minor problems, mere details to be cleaned up. No one imagined that within a few years, a young patent clerk would overthrow the very foundations of physics and reshape humanity's understanding of space, time, and reality itself. Sources used: Einstein, His Life and Universe by Walter Isaacson, pages 315. The Oxford Companion to the History of Modern Science, edited by J. L. Heilbronn, pages 262–265. Subtle is the Lord by Abraham Pais, pages 111–118. Einstein 1905, The Standard of Greatness by John S. Rigdon, pages 312. Part 2, Childhood, Education and Early Struggles. Albert Einstein was born on March 14, 1879 in Ulm, a city in the Kingdom of Württemberg in the German Empire. His father, Hermann Einstein, ran a small electrochemical factory with his brother. His mother, Pauline Koch, came from a prosperous merchant family. The family was Jewish but not religiously observant, embracing a secular middle-class life. When Albert was 1 year old, the family moved to Munich, where his father and uncle established an electrical engineering company, manufacturing dynamos and electric lights for street illumination. Contrary to popular myths, Einstein was not a poor student who failed mathematics. This legend appears to have originated from confusion about the grading system in different schools. He excelled in mathematics and physics from an early age. At age 12, he taught himself Euclidean geometry from a textbook and later described it as a formative experience. He did, however, clash with the authoritarian teaching methods common in German schools. He found the rigid discipline and rote memorization stifling. His independent spirit and questioning nature often irritated his teachers. In 1894, Hermann's business failed, and the family moved to Italy, leaving 15-year-old Albert behind to finish his education. Unhappy and isolated, Einstein obtained a medical certificate claiming nervous exhaustion and left school without graduating. He joined his family in Pavia and spent several months hiking in the Italian countryside. In 1895, he attempted to enter the Swiss Federal Polytechnic School in Zurich without a secondary school diploma. He passed the mathematics and physics sections brilliantly, but failed the general section. He completed his secondary education at a progressive school in Aarau, Switzerland, where teaching methods emphasized visual thinking and independent inquiry, an approach that suited him well. Einstein entered the Polytechnic in Zurich in 1896. He studied physics and mathematics but often skipped lectures, preferring to study on his own. He read the latest physics journals and original papers by Maxwell, Boltzmann, and other leading scientists. His friend Marcel Grossmann took meticulous notes that Einstein borrowed before examinations. In 1900, Einstein graduated but with undistinguished grades. His independent behavior had alienated some professors, particularly Heinrich Weber, who refused to write him a recommendation. For 2 years, Einstein struggled to find employment. His applications for academic positions were rejected. He survived on temporary teaching jobs and tutoring. In 1903, he married Milva Marek, a fellow physics student he had met at the Polytechnic. The couple had already had a daughter, Liesl, in 1902, whose fate remains uncertain. Historians believe she was either adopted or died in infancy. In 1902, with help from Marcel Grossmann's father, Einstein secured a position as a technical expert third class at the Swiss Patent Office in Bern. The job required him to evaluate patent applications for electromagnetic devices. It provided financial stability and, surprisingly, left him time to think about physics. He would later describe the patent office years as among the most productive of his life. Sources used: Einstein, His Life and Universe by Walter Isaacson, pages 1689. Einstein, A Biography by Albrecht Fersing, pages 19-127. The Collected Papers of Albert Einstein, Volume 1, pages Roman 17, Roman 25. Subtle is the Lord by Abraham Pies, pages 37-45. Part 3, The Miracle Year of 1905. By 1905, Einstein had been working at the Swiss Patent Office for 3 years. His responsibilities involved analyzing technical specifications for electrical machinery, work that sharpened his ability to identify fundamental principles. After his 8-hour workday, he devoted evenings and spare moments to theoretical physics. He discussed ideas with a small group of friends he called the Olympia Academy, reading philosophy and science together. During this period, with no access to laboratories, no research collaborators, and no academic position, Einstein produced 4 papers that revolutionized physics. The first paper, completed in March, addressed the photoelectric effect, a phenomenon in which light shining on metal surfaces ejects electrons. Classical physics treated light as a continuous wave, but this could not explain experimental observations. Einstein proposed a radical solution. Light itself consisted of discrete packets of energy, later called photons. Each photon carried energy proportional to its frequency. When a photon struck an electron in the metal, it transferred its energy instantaneously. This quantum hypothesis contradicted Maxwell's wave theory and challenged the foundation of 19th century physics. The idea was so revolutionary that many physicists, including Max Planck, who had pioneered quantum theory in a limited form, initially rejected it. The second paper, submitted in May, provided mathematical proof that atoms and molecules exist. This may seem obvious today, but at the time, some prominent scientists still doubted atomic theory. Einstein analyzed Brownian motion, the random jittering movement of pollen grains suspended in water, first observed by botanist Robert Brown in 1827. Einstein showed that this motion resulted from collisions with invisible water molecules. His equations made specific predictions about the relationship between particle size, temperature, and movement. When experimental physicist Jean Perrin confirmed these predictions in 1908, the reality of atoms became undeniable. The third paper, submitted in June, introduced special relativity. Einstein confronted the contradiction between Newton's mechanics and Maxwell's electromagnetism. Maxwell's equations implied that light traveled at a constant speed, but constant relative to what? Experiments had failed to detect the ether, the hypothetical medium supposedly carrying light waves. Einstein made a bold assumption. The laws of physics are the same in all inertial reference frames, and the speed of light is constant for all observers regardless of their motion. From these two postulates, he derived astonishing consequences. Space and time were not absolute but relative, depending on the observer's motion. Events that appeared simultaneous to one observer might occur at different times for another. Moving clocks run slower. Moving objects contract in the direction of motion. These effects became significant only at speeds approaching light speed, which is why they had never been noticed in everyday life. In a short follow-up paper submitted in September, Einstein derived the most famous equation in physics, E equals mc2. Energy and mass were equivalent, related by the square of light speed, an enormous number. A tiny amount of mass could be converted into tremendous energy. This relationship would later explain the power source of stars and, tragically, enable nuclear weapons. These 4 papers appeared in Annalen der Physik, a prestigious German physics journal. Einstein had submitted them from the patent office, signing as A. Einstein Bern. Their impact was not immediate. Special relativity in particular took years to gain acceptance. Most physicists found the ideas too strange. The revision of fundamental concepts like absolute time seemed unnecessary. Yet within a decade, experimental evidence and mathematical elegance would compel the scientific community to accept that a patent clerk had overthrown Newton and revealed a stranger, more beautiful universe than anyone had imagined. Sources used: Einstein 1905, The Standard of Greatness by John S. Rigdon, pages 15142. Subtle is the Lord by Abraham Pais, pages 148-196. The Collected Papers of Albert Einstein, Volume 2, pages 134-166, 223-274. Einstein, His Life and Universe by Walter Isaacson, pages 90-141. Ideas and Opinions by Albert Einstein, pages 290-323. Part 4, General Relativity and Worldwide Fame. Special relativity had revolutionized physics, but Einstein recognized its limitation. It applied only to objects moving at constant velocity, not to acceleration or gravity. Between 1907 and 1915, he worked toward a more general theory that would incorporate gravity into the relativistic framework. This became the most difficult intellectual challenge of his life. In 1907, Einstein experienced what he later called the happiest thought of my life. He imagined a person falling freely from a roof. During the fall, the person would feel weightless, unable to sense their own weight. This insight suggested a deep connection between acceleration and gravity. A person in an accelerating elevator would feel pressed to the floor, indistinguishable from standing in a gravitational field. Einstein called this the equivalence principle. Acceleration and gravity are locally indistinguishable. Developing this insight into a complete theory required advanced mathematics beyond what Einstein had learned. He turned to his former classmate Marcel Grossmann, now a mathematics professor, who introduced him to the tensor calculus and non-Euclidean geometry developed by mathematicians like Bernhard Riemann and Gregorio Ricci-Bastro. Einstein realized that gravity was not a force in the Newtonian sense, but a curvature of space and time itself. Massive objects like stars and planets warp the fabric of spacetime, and other objects follow curved paths through this warped geometry. The mathematics was formidable. Einstein made several false starts. He published preliminary versions that contained errors. Competing physicists, including the brilliant mathematician David Hilbert, were pursuing similar ideas. In November 1915, Einstein finally arrived at the correct field equations for general relativity. These 10 interrelated differential equations described how matter and energy curve spacetime and how this curvature determines the motion of matter. He immediately applied them to a long-standing puzzle, the anomalous precession of Mercury's orbit. Newton's gravity could not fully explain why Mercury's elliptical orbit slowly rotated. General relativity predicted the exact observed value. Einstein later recalled that when the calculation matched observation, he felt something like a physical sensation in his chest. General relativity also made a bold prediction. Light passing near a massive object should bend due to spacetime curvature. The amount of bending differed from the smaller deflection predicted by Newtonian gravity. Einstein calculated that starlight grazing the sun's edge should deflect by 1.75 arcseconds, a tiny but measurable angle. Testing this required observing stars near the sun during a total solar eclipse. World War I delayed such observations, but in 1919, British astronomer Arthur Eddington led 2 expeditions to observe a solar eclipse, one to the island of Princeton off West Africa and another to Sobral in Brazil. Despite difficult conditions and questionable photographic plates, Eddington's analysis supported Einstein's prediction. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The Times of London proclaimed revolution in science and Newtonian ideas overthrown. Overnight, Einstein became an international celebrity. The timing mattered. World War I had devastated Europe. The fact that British scientists had confirmed the theory of a German physicist symbolized the transcendence of science over national hatred. Einstein's exotic theory of curved spacetime captured public imagination. Newspapers struggled to explain relativity, often inaccurately. Einstein's distinctive appearance, wild hair and thoughtful eyes, made him recognizable worldwide. In 1921, Einstein received the Nobel Prize in Physics. Surprisingly, the citation was for his 1905 paper on the photoelectric effect, not for relativity. The Nobel Committee considered relativity still somewhat controversial and wanted more experimental confirmation. Some historians also note potential anti-Semitism and political considerations. Einstein did not attend the ceremony, traveling instead to Japan. He would later acknowledge that general relativity was his greatest achievement, but the photoelectric effect had proven more immediately useful and easier to verify experimentally. Sources used: Einstein, His Life and Universe by Walter Isaacson, pages 140–287. Subtle is the Lord by Abraham Pies, pages 212–261. No Shadow of a Doubt by Daniel Kennefic, pages 87–198. Einstein, A Biography by Albrecht Ferlsing, pages 374–478. The Collected Papers of Albert Einstein, Volume 6, pages 98–158. Part 5, Politics, Exile, and the Atomic Age. Einstein's fame coincided with political turmoil in Germany. After World War I, the Weimar Republic faced hyperinflation, political extremism, and growing anti-Semitism. Einstein, by now a professor at the University of Berlin and director of the Kaiser Wilhelm Institute for Physics, became a target for nationalist and anti-Semitic attacks. Some German physicists, including Nobel laureates Johann Stark and Philipp Lenard, denounced relativity as Jewish physics and organized public campaigns against Einstein. Einstein responded by embracing his Jewish identity more strongly. Though not religious, he became an advocate for Zionism, supporting the establishment of a Jewish homeland in Palestine. He worked with Chaim Weizmann to raise funds for Hebrew University in Jerusalem. He traveled extensively, lecturing in the United States, Britain, Japan, and Palestine, both to promote science and to support Jewish causes. He also advocated for pacifism and international cooperation, positions that made him controversial during the nationalist fervor of the interwar period. When Adolf Hitler became Chancellor of Germany in January 1933, Einstein was visiting the United States. He immediately understood the danger. In March 1933, Nazi authorities raided his summer cottage and his Berlin apartment, confiscated his property, and formally revoked his German citizenship. Einstein renounced his position at the Prussian Academy of Sciences and never returned to Germany. His books were among those burned in Nazi book-burning ceremonies. Propaganda denounced him as a symbol of dangerous Jewish intellectualism. Einstein accepted a position at the newly established Institute for Advanced Study in Princeton, New Jersey. He settled into a modest house on Mercer Street, where he would live for the remainder of his life. He became an American citizen in 1940 while retaining his Swiss citizenship. Princeton provided a haven, but Einstein watched with horror as Nazi Germany expanded across Europe and intensified persecution of Jews. In the summer of 1939, physicists Leo Szilard and Eugene Wigner visited Einstein in Long Island, where he was vacationing. They explained recent discoveries about nuclear fission. Splitting uranium atoms released enormous energy, exactly as predicted by E equals mc2. They feared Nazi Germany might develop an atomic bomb. After some hesitation, Einstein agreed to sign a letter to President Franklin D. Roosevelt warning of this danger and urging American research into nuclear weapons. The letter, delivered in October 1939, helped initiate what became the Manhattan Project. Einstein's actual involvement in the bomb's development was minimal. His security clearance was denied because of his pacifist activities. He contributed no scientific work to the project. Physicist J. Robert Oppenheimer, who directed the Los Alamos laboratory, never consulted him. Einstein's role was limited to that initial letter, yet it became one of the most consequential acts of his life. He later expressed regret, telling Linus Pauling, "I made one great mistake in my life when I signed the letter to President Roosevelt recommending that atom bombs be made." When atomic bombs destroyed Hiroshima and Nagasaki in August 1945, Einstein was deeply shaken. He had not expected the weapon to be used on civilian populations without warning. For the remainder of his life, he became an outspoken advocate for nuclear disarmament and world government. He chaired the Emergency Committee of Atomic Scientists, which sought to educate the public about nuclear dangers. He argued that only international control of atomic energy could prevent catastrophic war. During the Cold War, his political activities attracted FBI surveillance. J. Edgar Hoover's FBI compiled a 1,427-page file on Einstein, monitoring his associations and public statements. Einstein spoke out on other issues as well. He supported the civil rights movement, calling racism America's worst disease. He befriended African-American singer Paul Robeson and corresponded with W.E.B. Du Bois. When physicist and civil rights activist W.E.B. Du Bois faced trial during the McCarthy era, Einstein offered to testify as a character witness, and the charges were subsequently dropped. Einstein refused to testify before the House Un-American Activities Committee, declaring that intellectuals should practice civil disobedience against such investigations. These positions made him controversial, but demonstrated his commitment to principles over popularity. Sources used: Einstein, His Life and Universe by Walter Isaacson, pages 288–505. Einstein, A Biography by Albrecht Fersing, pages 605–752. The World as I See It by Albert Einstein, pages 114–142. Ideas and Opinions by Albert Einstein, pages 828, 114–120. The FBI's Files on Einstein, Declassified Documents, National Archives. Part 6, Later Scientific Work and Personal Life. While Einstein's political activism occupied much of his later years, He never stopped pursuing physics. His primary scientific goal from the 1920s until his death was developing a unified field theory that would unite gravity and electromagnetism in a single mathematical framework. He hoped to extend general relativity to encompass all fundamental forces, creating a complete theory of nature. This quest proved frustrating. Einstein published numerous papers proposing different mathematical approaches, but none succeeded. The problem was more difficult than he anticipated, partly because physicists were discovering additional forces and particles that Einstein's framework did not accommodate. The strong and weak nuclear forces, unknown in Einstein's early career, could not be ignored. Moreover, Einstein's approach increasingly diverged from mainstream physics. The central scientific debate of Einstein's later life concerned quantum mechanics. Throughout the 1920s, physicists including Niels Bohr, Werner Heisenberg, Max Born, and Erwin Schrödinger developed quantum theory into a comprehensive framework describing atomic and subatomic phenomena. This theory was extraordinarily successful experimentally, but its interpretation troubled Einstein deeply. Quantum mechanics described physical properties in terms of probabilities rather than certainties. According to Heisenberg's uncertainty principle, certain pairs of properties like position and momentum could not both be precisely determined. Bohr argued that observation itself affected quantum systems, making objective reality impossible to separate from the act of measurement. Einstein found this philosophically unacceptable. He believed physical reality existed independently of observation. God does not play dice with the universe, he famously declared, though he later clarified that his objection was not to probability itself, but to the idea that probability was fundamental rather than a limitation of incomplete knowledge. In 1935, Einstein and colleagues Boris Podolsky and Nathan Rosen published a paper presenting a thought experiment now known as the EPR paradox. They argued that quantum mechanics was incomplete because it could not account for what Einstein called spooky action at a distance, correlations between distant particles that seemed to require instantaneous influence. Einstein debated Bohr repeatedly at conferences and in correspondence. These debates were conducted with great mutual respect, though neither convinced the other. Most physicists sided with Bohr. Quantum mechanics worked brilliantly for practical calculations, while Einstein's objections seemed philosophical rather than scientific. In subsequent decades, experiments testing quantum entanglement largely vindicated quantum mechanics, though the philosophical questions Einstein raised remain subjects of debate. Einstein's personal life during the Princeton years was quieter but not without complexity. His marriage to Milva Maric had ended in divorce in 1919. He married his cousin Elsa Lurwenthal the same year. Elsa died in 1936. Einstein lived thereafter with his secretary Helen Dukas and Elsa's daughter Margit. His son Hans Albert, who became a successful engineer, immigrated to the United States and maintained contact. His younger son Eduard suffered from schizophrenia and spent most of his adult life in psychiatric institutions in Switzerland. Einstein supported him financially but rarely saw him, a source of sadness that biographers note Einstein rarely discussed. Einstein maintained friendships with other scientists and intellectuals. He enjoyed sailing, though he never learned to swim. He played the violin throughout his life, favoring Mozart and Bach. Visitors to his home often found him in casual dress, sometimes without socks, an informal manner that endeared him to some and puzzled others. He received thousands of letters from strangers seeking advice, help, or simply wishing to correspond with a famous genius. Helen Dukas managed this correspondence, though Einstein personally answered letters from schoolchildren and occasionally from fellow physicists. In April 1955, Einstein experienced severe abdominal pain. Doctors diagnosed a ruptured abdominal aortic aneurysm. He refused surgery, saying, "I want to go when I want. It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." He was admitted to Princeton Hospital, where he continued working on equations for his unified field theory until the end. He died early in the morning on April 18, 1955, at the age of 76. Following his wishes, his body was cremated and his ashes scattered in an undisclosed location. His brain was removed for study without family permission, a controversial decision that remains ethically questionable, but reflected the extraordinary reverence with which he was regarded. Sources used: Einstein, His Life and Universe by Walter Isaacson, pages 451–540. Subtle is the Lord by Abraham Pais, pages 440–462. The Born-Einstein Letters, pages 170–223. Out of My Later Years by Albert Einstein, pages 53–94. Einstein, A Biography by Albrecht Fersing, pages 687–763. Part 7, Legacy and Historical Importance. Albert Einstein's legacy extends across physics, philosophy, technology, and culture. His scientific contributions fundamentally altered humanity's understanding of reality. Special relativity revealed that space and time are interwoven, dynamic rather than absolute. General relativity showed that gravity is geometry, the curvature of spacetime itself. These insights provided the foundation for modern cosmology, including theories of the Big Bang, black holes, and the expanding universe. Every astronomical observation that probes the distant universe, every gravitational wave detection, every test of cosmological models relies on Einstein's equations. The practical applications of relativity are not merely theoretical. The global positioning system, used daily by billions of people for navigation, must account for both special and general relativistic effects. Satellites orbit at high speeds where time runs slightly slower due to velocity, but they also experience weaker gravity where time runs slightly faster. GPS calculations must correct for both effects, differing by about 38 microseconds per day. Without these corrections, GPS positions would drift by several kilometers daily, rendering the system useless. Einstein's work on the photoelectric effect helped establish quantum theory, which underpins modern electronics, chemistry, and materials science. Semiconductors, lasers, transistors, and computer chips all depend on quantum principles that Einstein helped discover. His proof of atomic reality through Brownian motion analysis provided essential validation for chemistry and molecular biology. His prediction of stimulated emission led to the development of lasers decades after his death. Perhaps equally significant was Einstein's impact on how humanity thinks about science and knowledge. He demonstrated that even the most fundamental, seemingly obvious assumptions, like absolute time, could be overturned by careful reasoning and attention to experimental evidence. His thought experiments, imagining riding alongside a light beam or observers in accelerating elevators, showed that physics could be explored through imagination guided by logic. He made conceptual clarity as important as mathematical technique. Einstein's public image shaped popular understanding of genius. His disheveled hair, penetrating gaze, and kindly demeanor became iconic. This image was both helpful and problematic. It inspired generations to pursue science, showing that profound understanding was achievable. Yet it also promoted an unrealistic notion of the lone genius, obscuring the collaborative nature of science and the years of disciplined work underlying creative breakthroughs. Historians of science recognize Einstein as one of the greatest physicists, comparable only to Isaac Newton and perhaps James Clerk Maxwell. Unlike Newton, who built upon Galileo and others, Einstein overturned existing frameworks. Unlike Maxwell, whose work was initially understood by few, Einstein explained his discoveries in ways that, at least in principle, a general audience could grasp. His ability to identify fundamental problems others had overlooked, to question basic assumptions, and to construct new conceptual frameworks set him apart. Yet Einstein was not infallible. His quest for a unified field theory failed. His resistance to quantum mechanics, while based on legitimate philosophical concerns, put him at odds with the direction physics took. His personal life included failed relationships, and by his own later acknowledgement, neglect of family responsibilities. Examining Einstein honestly, recognizing both achievements and limitations, provides a more accurate and ultimately more inspiring portrait than hagiography. Einstein's political legacy remains complex. His advocacy for peace, civil rights, and nuclear disarmament reflected moral courage but sometimes lacked practical effectiveness. His support for Zionism contributed to the establishment of Israel, yet he warned against nationalism and advocated for coexistence with Palestinians, positions that satisfied neither side completely. His willingness to sign the letter initiating the Manhattan Project, despite his pacifism, showed the moral ambiguity inherent in scientific responsibility. More than 6 decades after his death, Einstein remains culturally ubiquitous. His image appears on posters, stamps, and advertisements. His name is synonymous with intelligence. Schools, streets, institutes, and even a chemical element bear his name. This popularity sometimes trivializes his actual contributions, reducing them to E equals MC2 on a t-shirt. Yet it also reflects something genuine, a recognition that understanding the universe at its deepest level represents one of humanity's highest achievements, and that Einstein reached heights of understanding few have equaled. The scientific community continues to test and extend Einstein's theories. Gravitational waves, predicted by General Relativity, were finally detected directly in 2015, a century after Einstein formulated the theory. These observations opened a new way of observing the universe, confirming Einstein's insights with unprecedented precision. Physicists continue seeking the unified theory that eluded Einstein, now attempting to reconcile general relativity with quantum mechanics. Whether such a theory exists and what form it might take remains unknown. But the questions Einstein asked and the methods he used to pursue them continue guiding physics today. Albert Einstein transformed human understanding of space, time, matter, and energy. He showed that the universe operates according to principles stranger and more beautiful than common sense suggests. He demonstrated that intellectual courage, disciplined reasoning, and imaginative thought experiments could reveal truths about reality that no experiment of his day could directly observe. He proved that fundamental physics, pursued with sufficient depth, could change not merely how we calculate but how we think. In doing so, he became not only one of history's greatest scientists, but also a symbol of the human capacity to comprehend the cosmos through reason and imagination. Sources used: Einstein, His Life and Universe by Walter Isaacson, pages 540–551. Subtle is the Lord by Abraham Pies, pages 477–501. The Cambridge History of Science, Volume 5, pages 614–629. No Shadow of a Doubt by Daniel Kennefic, pages 240–267. Ideas and Opinions by Albert Einstein, pages 270–289.